October 23, 2019, Google announces it has achieved the impossible goal of quantum supremacy, a machine more than 100 million times faster than your 16-inch MacBook. Only 1 month later, AWS releases quantum computing as a service in the cloud. If you're a software developer in today's world, there's a good chance your infrastructure is on the cloud, and very likely with a big provider like AWS, Azure, GCP, or IBM. 90% of companies are on the cloud, 60% of workloads run on the cloud, 30% of IT budgets are allocated to the cloud, generating hundreds of billions of dollars in revenue, and those numbers are only expected to increase in the coming years. In today's video, you'll learn exactly what cloud computing is, why companies are adopting it so rapidly, and what you need to know as a software developer. If you're new here, like and subscribe, and you can follow along with the full write-up on Fireship.io. Cloud computing is a win-win, both for companies that provide the services and the companies that use them. The providers make tons of money. In fact, AWS makes up more than 13% of Amazon's total sales and operates at a much higher profit margin than its retail business. But it's also a huge win for their customers. Instead of buying and managing its own hardware, a startup today has all the infrastructure it could possibly need right at its fingertips. The startup only pays for what it actually uses, it takes almost no effort to scale things up or down, and you don't need to hire an IT guy to wire the thing up. I mean, imagine if I tried to build a server room here in Phoenix, Arizona. My air conditioning bill alone would likely far exceed whatever my AWS bill would be for the same set of resources. That's because they build these highly optimized cloud campuses next to rivers to optimize cooling, with state-of-the-art equipment that can guarantee uptimes of 99.99% and beyond. I like to think of cloud computing like a power plant. You don't care where or how that power is being generated, you just plug in your device and then pay the bill. In fact, we might as well just call that electricity as a service. Because as a developer, it's important to distinguish between the different categories of cloud services out there. The modern cloud can trace its roots back to 2006, when Amazon launched EC2 and S3. EC2 stands for Elastic Compute Cloud, and it's essentially a virtual computer with its own RAM and CPU, along with an operating system you can administer and an IP address for networking. When you spin up a server in the cloud, it's called a virtual machine, because you haven't actually allocated any specific piece of hardware. Rather, the cloud has virtualized a simulated environment for you that resembles a piece of hardware. There's a lot going on behind the scenes to make this possible that you don't really need to know, like how they use hypervisors on top of bare metal to handle CPU scheduling and memory allocation. The other big service launched by AWS back in 2006 was S3, which is basically a hard drive with a file system in the cloud where you can store things like images and videos. Things like storage buckets and virtual machines are known as infrastructure as a service. They're the low-level building blocks of the cloud, so it's up to the developer to manage and scale them. Once infrastructure became available, it created explosive growth in a new type of software as a service. A great case study is Dropbox. In the early days, the company didn't have the money to roll out its own infrastructure, so it uploaded its users' files to S3. So it didn't even really start out as a file storage company, it was more of a software company that helped people get their files uploaded to the cloud. And it just goes to show you that you can build a billion-dollar business by focusing primarily on the front-end user experience. So infrastructure as a service abstracts away hardware. It took no more than a couple of years to see cloud computing rise to another level, a platform as a service. When developing an application, developers have a lot more concerns than just hardware. You have to think about security and how to scale the workload, and how to put all the pieces together into a cohesive unit. That's what a platform as a service aims to do. Some famous examples include Elastic Beanstalk, Heroku, and Google App Engine. Let's imagine a developer has built an app with Ruby on Rails. In order to be used by people around the world, that app will need a database and a web server with a very specific configuration. The platform is designed to take care of the configuration part. In theory, the only thing the developer has to do is upload their code, and the cloud takes care of the provisioning of the database, provides security, and scales the traffic. So what we have here is a platform for creating software as a service. But we can still take things one step further. The cloud can also provide SDKs that bring the cloud directly into our front-end applications. And that means a developer might not need any back-end code at all, giving us a back-end as a service. The two big players in this space include Firebase from Google and Amplify from AWS. With just a few lines of JavaScript, anybody can create a real-time application with user authentication hooked up to a cloud database that's way more reliable than any back-end you would build from scratch. Sounds awesome, but it's not without its drawbacks. The more you rely on services offered by a given cloud, the more likely you are to experience vendor lock-in. The cloud can help you get your software off the ground, but once you become successful, like Dropbox, your opinion might start to change. In 2016, Dropbox started to move their customers' data off AWS to their own data centers, and cut at least $75 million from their operating expenses. In this case, it made sense to move off the cloud to on-premises. But they're actually not fully on-prem. They still use the cloud to handle about 10% of their file uploads, especially for edge cases in regions that their data centers don't cover. And that's what we call a hybrid cloud. It generally refers to big enterprises that run a private cloud on their own data centers, but also combine it with services on the public cloud. And by public, I mean the cloud where you can just sign up with an email address and credit card and start doing stuff. You might also hear the term multi-cloud. This refers to a single architecture or application that combines services from multiple public clouds, usually to prevent things like vendor lock-in and optimize pricing. Now let's go ahead and jump into the cloud and take a look at some of its capabilities. We already talked a little bit about virtual machines and cloud storage buckets, but that's just the tip of the iceberg in today's world. AWS alone offers more than 150 different services and APIs. But one thing all these services share in common is a service level agreement, or SLA. This is a contract between you and the cloud provider. The provider generally guarantees a certain uptime and error rate for the service, and will generally provide a financial credit or refund back to the client if it fails to meet those SLA requirements. On the other side of the coin, the client generally has a quota that they must stay within when using the service. Sometimes I like to say the cloud scales infinitely, but I don't mean that to be taken literally. The quota tells you how far you can push the limits. When getting started with a cloud provider, a great place to start is with identity and access management. The opposite of who am I am. It's the front gate to your infrastructure, and you shouldn't just let anybody in. You can secure your services by attaching security policies to them. For example, you might have a storage bucket, and that policy controls who in the organization can actually access the files inside it. Now, if your organization has thousands of employees, it would be very cumbersome to manage policies for every single resource. That's where roles come in. They allow you to group permissions together into a unit that can be reused throughout the cloud. And you can assign roles outside of your account if you're working with consultants or some other third party. Now, in some cases, your machines might need to communicate with each other. For that, you can define resource-based policies or service accounts. This would allow a virtual machine, for example, to access a database somewhere else in your cloud. Now that we know a little bit about security, let's take a look at the backbone of the cloud, compute resources. On Google Cloud, we can create a virtual machine with Compute Engine. It will give you some options when you create this machine. The region represents the actual physical location of the data center. A region closer to your end users should be faster, but some companies must follow data residency regulations, which dictate where customer data can actually be stored. Now, each region is actually a campus with multiple isolated data centers. That means if you have a mission-critical workload, you can put it in the same region in multiple zones. If a meteor destroys one of those data centers, you'll still have a reliable service in that region. That gives you high availability and redundancy. Azure actually has the most data centers of all the clouds, and they have 2 secret government locations that we don't even know about. The next option is the machine type, which defines the amount of memory and CPU in this virtual machine. The bigger they come, the more they cost. But the great thing about the cloud is that everything is pay as you go. You're billed down to the second, and you can shut the instance off at any time. From there, you need to determine the operating system by selecting a disk image. You have a bunch of different flavors of Linux or Windows to choose from. From there, you can specify a service account if you have other services that need to access this VM. By default, you have a firewall that makes this instance inaccessible to the outside world. But we can change that by allowing HTTP traffic. Now, when it comes to networking, it's important to understand that the instance has an internal IP address and an external IP address. Both of these values are ephemeral or short-lived by default. That means if you rebuild the instance, it could be assigned a new IP address. However, if you have a service that relies on an IP address, you can reserve a static one. So what's the difference between an internal and an external IP? The internal version can only be used to communicate with other compute instances on the same cloud. If you need to communicate with other services on the internet, then you'll use the external IP. When it comes to networking, you might come across these weird terms, egress and ingress. Egress defines outbound data that's being sent from your instance to the outside world. Ingress is the exact opposite, data that's being sent from the outside world into your instance. Egress is typically the one to watch out for because it can have an impact on your bill. Now remember, we're just talking about a simulated computer here. If we want to access the command line for that instance, we can do so directly in the console with a Cloud Shell session. And inside the session, you can do pretty much anything you could do in a regular Linux or Windows terminal. So now that you know all this stuff about virtual machines, it's time to let you in on a little secret. For most applications, it's pretty rare to create them manually like I just showed you. There's just better ways to handle your compute resources. And a lot of it has to do with the way that they scale. Let's imagine we built an app on this VM, it's popular, and now our users are maxing out the CPU and memory on the instance. One option would be to scale it vertically. We could do that by adding additional CPU cores and more memory. to make this single VM more powerful. But we can only do that to a certain extent, so another option is to scale horizontally. Instead of making our VM bigger, we'll just create more of them. We can create them in regions all over the world and then distribute the workload accordingly. When you distribute VMs like this, you also need to worry about load balancing. You don't want all of your traffic going to a single VM while the others are just sitting there idle. But all of the clouds offer load balancer services to help you manage this stuff. But what if you never had to worry about scaling your infrastructure at all? Well, there are actually already two cloud computing paradigms that make that possible today. The first one we'll look at is containerization. Now, a container provides a way for you to simulate an operating system. That may sound very similar to a virtual machine, but there's one key difference.
You're inside a simulation of a simulation inside another giant simulation.
A virtual machine sits on top of the hardware directly, but a container sits on top of an underlying operating system to simulate another operating system or application. This is a really awesome thing for development because it means you can put your application in a container and then take it and deploy it to any cloud you want. Or in other words, you avoid the vendor lock-in. All of the clouds have container registries where you can upload your containers and then use them across other services. Now, most companies using this strategy have multiple containers to run different services. You might have one container for your Node.js web server, another for sending email, and another for training your machine learning algorithms. And as your business becomes more complex, you'll need a way to orchestrate all of these microservices. And that's where Kubernetes comes in. It organizes all of your containers into groups of pods. Then it can automatically scale those pods up or down based on the amount of traffic or utilization. When the traffic goes up, Kubernetes will allocate more virtual machines to run more containers. When the traffic dies off, it'll shut down those virtual machines so they're not sitting there idle, costing you money. But there's a great saying about Kubernetes, and it goes something like, why are you f***ing around with Kubernetes? Because in 2020, we have serverless, or functions as a service. It was first introduced in 2014 with AWS Lambda. It allows you to run code in response to events, like a regular HTTP request, or when something happens in some other cloud service, like a write to the database. The code you deploy to one of these functions will scale automatically, so you never have to worry about containers, VMs, or anything like that. And it's truly pay-as-you-go, because you only pay for each individual function invocation. Now, prior to 2019, the big trade-off was that you had no control over the actual runtime. So if you needed to install some OS-level software, you wouldn't be able to do that. But just in the last year or so, AWS released the Runtime API, and Google released a service called Cloud Run. And that means today we can do pretty much anything we want in a serverless environment. There are still some other trade-offs, but generally speaking, it's the easiest, most cost-effective way to deploy back-end code that scales. And I think that's pretty much everything you need to know about the compute in cloud computing, at least until we have quantum computers in the cloud. Oh wait, I almost forgot. It's 2020, we have those things already. I'm gonna go ahead and wrap things up there. If you learned something, please like and subscribe, and if you wanna see more videos like this, let me know in the comments. Thanks for watching, and I will talk to you soon.